We can get started. So, hello everyone. Welcome to the One World Combinatorics Onwards seminar. Our speaker today is Bastiàn Espinoza, and he is going to speak to us today about the Thue-Morse word in base 3/2.
Thank you, Narad. So let me start by saying that this is a joint work with my colleagues Julien Cassegne, Michel Rigaud, and Manon Stipulanti. And as you were saying, Narad, I want to discuss Thue-Morse word, but in a weird numeration system. So I'm going to start by defining these automatic words. From a very intuitive point of view, an automatic word is defined by using two elements. We're going to define numeration systems. And then we're also going to use a model of computation, in this case, automata. So a numeration system is something very intuitive. For instance, the base 2 numeration system is this idea of the fact that we can use powers of 2 to represent any non-negative integer. So in this case, we represent n as a finite sum, where these digits are elements of 0, 1. So they can be either 0 or 1. And it is well known that there is a unique such expansion. So we call this the base 2 expansion, and with this we obtain for every non-negative integer a finite string of symbols in this alphabet 0, 1. So this is the first element, a numeration system, and then we also have a model of computation. Here we're going to use automata. This is one of the simplest model of computations. They are defined by saying that these are machines that can compute with the restriction of using only a finite and bounded amount of memory. Because of that, they have a finite number of possible states. That's why they are also called finite state machines. I'm not going to enter into the details. I'm going to rather focus on a particular example, which is the machine that I call add2. And what this machine does is simply it takes an input. For instance, we can take the expansion of a number in base 2, and it returns the sum of these elements, which are zeros and ones. These are numbers as well, but it performs the sum modulo 2. And this is something that can be performed by a finite automaton because we only need one bit of memory. We only need to remember whether we have read an even number of ones or an odd number of ones at each time. Okay, so with this we get for each n a number which we interpret as a symbol. It can be either the symbol 0 or the symbol 1. And in this way we get an infinite word when we concatenate all these symbols. And this is the classical Thue-Morse word. So this is a word that has been studied a lot. It has connection with many different areas. What's important for us is to say that it is aperiodic. It is uniformly recurrent. We can, for instance, check some combinatorial structure of the language, the set of factors that appear here. We can also study frequencies of factors and so on. But now here in this talk, we want to consider a variation of the Thue-Morse word. We're going to use the same model of computation, the same machine, in fact, add2. The only difference is that we're going to use the base 3/2. And this is a bit tricky to define. So I'm going to directly state first what I meant by base 3/2. So it can be proved that every non-negative integer can be represented as a sum of this type. So be careful because here we're using powers of 3/2, and then we multiply one by 1/2. And also the digits that we use here, this time they can be 0, 1, or 2. And this is a bit weird to define. It is not the same numeration system as the beta numeration system associated to this number 3/2. But it is natural to consider this because as it was shown by Akiyama, Frugny, and Zakharovich in 2008, well, it was them who introduced this numeration system, and they used these numeration systems to study some difficult questions in number theory, mostly related to the equidistribution of powers of rational numbers modulo 1. And particularly, we're focusing on what we call Mahler's Z numbers, and there is a problem related to them. For us, we're going to, for just the moment, say and state that there is a unique way of representing non-negative integers with these restrictions. So digits are 0, 1, and 2. Okay, so we have this new numeration system, and from that we can also define an infinite word using the same machine as before, sum modulo 2. And the result is what we call the 3/2 Thue-Morse word. And this is the object that we want to study. We're going to really focus on this example. Of course, this belongs to a larger classes of words that we can consider by the same means, 3/2 automatic word, but this is a highly unexplored direction, so we're going to focus on this example as a guiding example. And we're going to see that many of the things that we discussed today generalize beyond this. Okay, here, more precisely, I want to start by stating a conjecture by Becking from 2020 or 2021. He made several conjectures, but we're going to focus for this talk on only two. In the paper, we have also addressed other conjectures of Becking. The first one is the fact that Becking conjecture based on some numerical experiments that T, the Thue-Morse word, is uniformly recurrent. And the second one is something about the frequencies. Again, by numerical experiments, they strongly suggest that the frequency of the symbol 0 occurs with frequency 1/2. So both letters occur with the same frequency. And our work here, what I'm going to present, is a confirmation of these two conjectures. We're going to prove that this is uniformly recurrent, and we're going to determine letter frequencies. But yes, as I was saying, there are many other natural questions and conjectures, both by Becking, natural questions that arise naturally after what I'm going to present here. Now, to study this word, we're going to take the point of view of substitutions. And more precisely, I want to define here what I call a skew substitution. Why do I want to do this? The general idea here is that thanks to a general theorem by Michel Manon, we know that any automatic word in a rational base is generated in some sense. We were going to say that it is the fixed point of a uniform skew substitution. And these are concepts that I'm going to define in a moment, but the point is that we can understand automatic word from the point of view of this skew substitution. Now, to define a skew substitution, we need first of all an action. We're going to start by an action of the monoid of words. So we fix an alphabet. We consider the monoid of words. This is a monoid, and it can act on a set that, in general, here we're going to consider a finite set. And then what we do is to consider a map of this type. So it takes an element of our set S, which we're going to consider to be a set of states, and then a word. And the output is another word. And we call this a skew substitution with respect to the action that we have just considered if it satisfies this equation. So let me just start by saying that the idea here is that, as I was saying, we have a state space, S, and when we apply this skew substitution, at each time that we read a letter, what we do is that we apply the substitution related to this state, and then we update the state. So we apply and update, apply and update. This is what this equation is saying. So for instance, in the first part, we have that we start with the initial state S, and we apply the substitution associated to this state to the first letter, B0. Then what we do is that we update the state by applying the action B0 to the state S. We get a possibly different state. And then from this state, we can apply a possibly different substitution to the second letter. And we continue like this. Now we update again with the letter B1 to the previous state. So we have B0, B1 now, and we continue applying up to the final letter. So apply and update. There are different ways of describing the same kind of things. I'm sure that some of you have already identified this as being essentially a transducer. And also from a more dynamical point of view, this can be seen related to skew products. And that's why I'm calling them skew substitution. So this is the language that we're going to use. Of course, these skew substitutions generalize the usual notion of substitutions, because if we consider, for instance, the trivial set, so a singleton, then the state does nothing, and we essentially recover the notion of substitution. So this is a it is a strict generalization of substitution. This is what I want to say. Now, the case we're going to consider can be seen as the simplest non-substitutive case. So the simplest case beyond the classical substitution case. So what we do is that we consider a state in which we only have two elements. We can interpret this as two states that are going to flip integers modulo 2. And the action is also the simplest that we can think of. The only thing that we do is that every letter acts in the same way by adding 1. So it flips the state. In a more intuitive way, what we're doing here is that when we apply a substitution, for instance, we apply substitution with some state with the state 0 to a word u, then the behavior of this action is saying we apply the substitution with state 0 at even positions, and then the substitution at with state 1, at odd positions. So this also, for this particular case, can be seen as what some people call a periodically iterated substitution. And now, before going to the examples, I need one last definition. I'm going to say that an infinite word is a fixed point for this for a particular skew substitution if we have the analog, the natural what we expect equation here. Of course, skew substitutions are defined on finite words, but as we do for classical substitutions, we can extend this definition to consider also infinite words in the natural way. So we want this kind of fixed point. What's important about fixed point is, as it happens with usual substitutions, in many cases, in the natural cases that we're going to consider, this kind of equation, the fixed point equation, can be used to reconstruct the whole infinite word by a single seed, which is typically a letter. And this is what is going to be the case here. So we say that a word is a fixed point in this case to mean essentially that we can generate the word from the substitution. That's why we can reduce kind of the problem of studying automatic words to a study of these uniform skew substitutions that come from the theorem of Michel Amann. Now, let me now give some examples. The first example is this substitution. The exact combinatorial data that is used to define the substitution is not that important. What is important is that the fixed point that we generate in this case is the Kolakowski word. So even if we consider very simple actions and very simple looking substitutions like the one that we have here, the word that we generate can be very complex. In particular, in this case, we know almost nothing about Kolakowski word. Most of the results that we have are conditional. If there is some previous hypothesis, then we can conclude things. But in general, it's a very complex problem, difficult to understand. We know very little. So we're very fast to complex problems. On the other hand, there are some more better behaved, there are better behaved examples. The second example that I want to present here is something that appears in the work of Julien Cassegne and Karumaki from 2003, more or less. They study what they call PQ tuplet words. This can be defined also using periodically iterated substitutions. They are related, of course, to tuplet subjects. And thanks to their work, it can be seen that these are also fixed points of these skew substitutions with some additional structure, but the point is that they are also covered by this formalism. These examples are already quite interesting because, for instance, they have a superlinear factor complexity, which goes already beyond to the classical examples of substitutive examples, for instance, or Sturmian subshifts and so on. And then as a kind of very bad behaved example as well, we have a paper by Andrulis and Hendricks in which they prove that also for these periodically iterated substitutions and hence for skew substitutions, we can construct words which have, for instance, exponential factor complexity. We can also construct words in which the language is undecidable. This means that, for instance, it could happen that for a single letter, we cannot decide using an algorithm whether this letter occurs somewhere in the infinite word. Now, in any case, these examples here go kind of in a different direction because they're highly non-recurrent, and we're going to focus mostly on examples that we expect to have high recurrence, a strong recurrence.
Can I ask a quick question?
Yeah.
So the undecidable example, does it require having like an infinite set or something?
No, it is a finite set, large set. I don't know how large, but it is a finite set.
Okay, somehow it's unintuitive that you can get something undecidable like this, but okay, maybe I'm missing something.
Check the paper. I don't remember the details, to be honest.
Okay, thank you.
Yeah, well. Oh, yes. So I was saying that. Yeah, I was saying that, so we have these bad examples, but now I want to focus on what we really want to study here, which is the Thue-Morse case. So as I was saying, we can generate the Thue-Morse case, the 3-half Thue-Morse infinite word using these skew substitutions, and the particular substitution that appears here is the following one. So we use only two letters, 0 and 1, and we use these two substitutions. So again, we come back to the case in which we use the very simple action in which every letter acts in the same way. We only flip the state. So we have a substitution for even coordinates, and then we have a substitution for odd coordinates. We use these two substitutions. It's not really important to look at the particular details. What is important about this is that we call this a uniform substitution. And this is very important. We call this an uniform substitution because for each state S, the length of the image depends on the state, but not on the letter that we're applying. In this case, we have length 2 and length 1. And this is something that happens, it is true for all automatic words in a rational base. We always can find representations of this form. So this is really something really important for us. It is not true, for instance, that for the Kolakowski word, we have this property. It is the opposite, in fact. The length depends on the letter, but not on the state. But yeah, so we have this substitution, and it generates the Thue-Morse word. So before going to further details, I just want to give a small example. Here I drew the Thue-Morse word. So it starts like this, 0, 0, 1, 1, 1, 0, 1, 1. And we can check that if we apply this substitution, we obtain the same prefix. So here the rule, what says is that at even coordinates, at even positions, what we do is that we duplicate the letter that is input. At odd positions, we invert the letter. So if we apply this rule to the zero position, this is an even position, so we duplicate the letter. Then in the next one, this is an odd position, we invert the letter. And then we duplicate, we invert, we duplicate, we invert, and so on. And we check that we generate the same prefix, but longer, of course. Okay. Now, the first set of results that I want to present here is this one. So the first thing to prove is, of course, that we indeed have that the Thue-Morse word is the fixed point of this particular substitution theta. This is a small computation because most of the work was already done by Dekin in a previous paper. But of course, this is something that we need to check. The second thing is that we can also estimate the factor complexity. In this case, it is given by this polynomial behavior, this polynomial exponent, where alpha is an irrational number that is greater than 2. And it's important that it is larger than 2, because again, it is very different to most of the examples that we can consider. In particular, this word cannot be morphic, because morphic words have at most quadratic complexity. And for the experts in the audience, I can also say that the dynamical system defined by this infinite word does not have infinite topological rank. And this, roughly speaking, means that we cannot generate this word even if we allow a finite number of different substitutions in the substituted structure that we would aim to construct. So in some sense, it is difficult to understand these systems from an aesthetic point of view, for instance. Okay, so these are very coarse things, but now we're going to focus on the last part, which is the fact that this word is uniformly recurrent, confirming the previous conjecture of Dekin that I explained. So this is the first, let's say, major result of the talk, uniformly recurrence, and then I'm going to discuss more about frequency. Now, I would like to discuss a bit the main tool or the main way we see things, because I think there is a lot of value here. So let me introduce what I'm going to call here a parity decoration. So what do we do is that we go back again to considering the Thue-Morse word, and we look at a prefix of this word. Since we want to study this from the substitutive point of view, what we want to do here is to iterate the substitutions, the skew substitution that we have in this case, so that after application and iteration of the substitution, we can obtain some asymptotic behavior We want to understand the combinatorics of iterating the substitution. But to do that, this is a bit tricky, because if you look at a random position, an arbitrary position of our infinite word, then we cannot directly apply the substitution. We need more information. We need to know whether we're looking at an even position or at an odd position. We solve this by adding what we call here parity decorations. So we're going to add a 0 to the first coordinate, to the first letter, because it occurs at an even position, and then to the second one, a 1, because it is an odd position, and we continue periodically like this. And now, after this decoration is added, we know how to apply the substitution to any given letter in our infinite word, because now we have the input letter, a 1, and the parity, a 0. So we know that we need to duplicate the letter with the 1, 1. But now the problem is that if we want to apply again this substitution, we cannot, because we don't have information about the parity here. So what we're going to do is consider also the parity decoration of the image. And then we're going to lift this parity to the previous level, so that at each letter in the previous level, we're going to add the decoration of the letter that is immediately below, like this. And with this, now we have that if we start from any given letter, we know that we need to apply the substitution at parity 0 for the first one. So we duplicate the letter and we get 1, 1. And then we know that we're at parity 0. So we know that we need to duplicate again. But of course, in the third step, we will not have enough information, so we need to do some. But for the moment, I just want to stress on the fact that it is completely unavoidable that we need to add these parities. Because, for instance, we can look at, I think, this position and also this position. Yes, if we look at these two positions, then we know that these two positions are at an even position because the blue decoration is 0. But their images are at an even position and at an odd position. In fact, we're going to see that all possible combinations appear. So we really need to deal with the fact that all possible combinations appear, and it is here that the complexity of this word appears. Yeah. I have one last figure for this. It doesn't matter. So in this figure, I have the same thing as before. This time I have the decoration in blue for the first one, the decoration in red for the second one, and then the decoration in green for the third one. So I just wanted to say that in this case, with 3 decorations, we can iterate 3 levels. Apply 3 times the substitution. What we're going to do is that we're going to, in fact, continue using these iterated, adding these iterated parity decorations forever. So now we're going to get a word, the Thue-Morse word with decorations, which at each position we have a letter, and this letter is equipped with a sequence, an infinite sequence of decorations. So now we have an infinite alphabet. This is going to, of course, pose a lot of problems, but the thing is that we know how to deal with those problems. Before that, I just want to point out that if we consider now, for instance, any position here, then the parity in the next step can be determined completely by the letter that we're reading at this position and the decoration sequence that we're reading. Why? Because for the first letter, the blue decoration, we know how the action of this is something that comes from the definition of our original action. We know that we always flip the first coordinate. For the second coordinate, the situation is a bit more tricky because it depends on the image that we see here. In this case, we know that the image is 1 because we know the blue decoration, and then we know how to compute the next red by simply flipping the red decoration. And this red lifts them to be the second coordinate here. And we continue like this forever. So the thing is that even if we have infinitely many decorations, a sequence of decorations, once we know the letter, we can compute the next sequence of decorations. And this is what we want to study. Now, formally, what we're going to do is say we consider the space here. And this is the set of parity sequences, the set of decorations that we can consider. And this process of determining the next decoration based on the letter defines an action in this infinite space. It is formally defined like this. It's a bit difficult to read, but as I was saying, in the first coordinate, we always flip the coordinate. This comes from the definition of the original action. And then in the next step, we need to first apply the substitution using the previous parity, and then use the action with respect to the word that we have here. So now we have the length of the image of this thing. And we can continue, but when we can continue, we need to iterate the substitution and things become okay. Now, what we can say in the particular case of the Thue-Morse substitution, and also for other automatic words in rational basis, is that I'm going to say it in these terms. This action T is conjugate to an odometer. So in more precise terms, it means that we have a commutative diagram of this type, where here we have the action that I was talking about before. Below, we have what we call an odometer, and this means that the base space is the set of two adic integers. And then we have an action that is simply adding one, as before, but we're adding one in a space that is much more complex as before, because this is an infinite space. This is a compact infinite space. And here, in this part, we have the same map at both sides, and this is a bijection. So in some sense, we're saying that up to some recoding, the action of T behaves as in the odometer. And we are going to use this representation. This is the same that contains most of the information for recurrence of, the topological recurrence, so the uniform recurrence part. It is worth mentioning that when we consider here the Kolakowski word, we can do kind of the same thing, but the space Z2 that we get here is not something as simple. Here we have an abelian group, essentially. In the Kolakowski case, we have something that is a profinite completion of the corresponding free group. Highly non-abelian, highly difficult to understand. It has many high-dimensional irreducible representations, and so on. Anyway, going back to the Thue-Morse case, we have that as a consequence of the theorem, and this is essentially a corollary, we can prove that T is uniformly recurrent. And many other properties that were implicit, some of the questions that were asked by Deakin, for instance. I don't want to go into these details, but these are in the paper. Okay. And this finishes also the second part. This is what I call the topological recurrence part. The last part is the second question of Deakin, the second conjecture of Deakin that I presented, and it's related to the study of frequencies. And studying frequencies is much more difficult, to be honest. It requires much more work than the previous part. So again, I'm going to here present results for the particular case of the Thue-Morse word with the mentality that we want to develop general techniques that work for other words and for more general situations and objects and so on. So that's why I'm going to start by saying that the first thing here is that if we're able to develop a general method for computing letter frequencies, then by using the classical sliding block construction, we can transform and translate the study of factor frequencies to the study of letter frequencies. So we're going to focus on this thing for the moment. We're going to say letter frequencies with aiming to obtain something general that also works later for factor frequencies. Of course, this can also be used to study, for instance, shift invariant measures of the associated dynamical systems, and well, similar objects, generic measures, and so on. Now, more precisely, what we want to show here for the study of letter frequencies is the theorem. I'm going to start with the theorem because it is a bit technical to describe. So what we're going to prove is something that is stronger than simply showing that the frequencies are the frequencies of both letters are the same. We need to be more precise. So we define this quantity first. This quantity depends on three parameters. It depends on the letter that we're going to look at. It depends on the level that I call this the level n, that is essentially a power of 2, and then a residue class I modulo this power of 2. And what we do is that we count occurrences of A, of this particular letter, but we sieve by a residue class, the residue class I mod 2 to the power of n. Then we also apply some normalization. We don't need to care about all these technicalities. And the theorem says that this limit exists. And moreover, the limit is equal to 1/2. So in more intuitive terms, we're saying that here we have an equidistribution of the letters across all residue classes for any power of 2. And yes, it is a complete equidistribution. And as we're going to see, this is something that is again related to the fact that we have this odometer, the Z2 odometer, playing a role behind. Of course, from this theorem, we can recover Dekker's conjecture because it corresponds to the case in which n equals a equals I equals 0. So the first level, when we apply the theorem to the first level, we record the fact that the frequency of 0 is 1/2. Okay, and now I would like to discuss a bit about the proof. One additional thing, yes. So this discuss a bit the proof, but as I was saying, is quite long and a bit technical. Involves some computations that are not difficult, but they cannot be presented here. And some technical steps. So one thing that I want to say now is that we're going to assume for the moment, just for the sake of the exposition, that frequencies exist. This is, of course, not trivial, but we have some tricks that say, as long as in the end of the proof we can show that there is a unique way of determining frequencies in some sense, then we can kind of assume that frequencies exist. So, assuming that frequencies exist, the proof goes more or less as follows. What we say is that first we start with the most naive idea, which is saying we're going to disubstitute and obtain a linear relation for the frequencies. This is what we do in the substitutive case. This is what we do in the static case, very classical idea. So we try to do this. And it is here that these sieved positions occur naturally. So the equation that we have, we do get an equation, is of this form. And this is what I'm going to call the Perron-Frobenius equation. So it depends here on the left-hand side on the level n. But on the right-hand side, we have a linear combination that depends on level n plus 1. So on the right-hand side, we need more information. We need residue classes modulo 2 to the power of n plus 1. Each time that we apply the recurrence, we lose a bit of this information. We need to decrease the power of 2 that we consider. Here we have some coefficients. These are coefficients that come from the particular combinatorics of the substitution. We don't care that much about them now. And, well, we have this equation. Now, the first question is whether this equation is enough. And the thing is that computational experiments suggest that this equation already forces the frequencies to be completely determined and to have the value that I was describing before. This is why we try to prove this theorem. So the informed guess for solving this equation is to say that this is the unique solution. And we're going to show that this is the case, in fact. Now, how do we do this? In the usual substitutive case, we want to use usually the Perron-Frobenius theorem. And the Perron-Frobenius theorem says that for non-negative matrices, for non-negative linear relations, as the one that we have here, there is some contraction phenomena that forces that any iterated linear recurrence like this one forces the equations to lie on a single one-dimensional space, and with that, we're done. In this case, we expect to observe the same phenomena, but the situation is substantially more difficult because at each level, at each n, we have a possibly different vector. So in level n, we have a vector that has 2 to the n plus 1 coordinates. We have 2 coordinates for the letters, and then we need more coordinates for each residue class. So this is, in some sense, an unbounded dimension problem. And even if in this setting, the Perron-Frobenius theory, the general theory of Perron-Frobenius, gives criteria and even characterizations on stating when we have this one-dimensional limiting direction, these criteria are very difficult to apply. And this is the difficulty. How do we check those criteria? The strategy then is to use the particular structure that we have in this problem. And this is the structure that comes from the fact that we're working with a skew substitution, an action, and the fact that we can describe this action as a two-adic odometer. So the general strategy here is that we're going to lift this Perron-Frobenius equation, the one in green, to the two-adic odometer. So all these levels lie in the same space. Then we're going to pass to Fourier domain. We're going to apply the Fourier transform, and I'm going to explain in a moment why this makes sense. And then in Fourier domain, we're going to prove a construction property for the associated operator. And this construction property will force to have a unique solution. And this is the construction that I was talking about before, that comes from, that is motivated by Perron-Fermat theory. Yes. So I'm going to give the overview. As I was saying, first we leave the odometer. So now we're going to transform the previous frequencies to functions that are defined on the odometer. We can see them as vectors. So we group all letters into this vector. And the definition is the expected one. So it is the vector in which now the Z, the entry in the two-adic odometer, simply defines the residue class in level M. This map is very well behaved. It is continuous. It is even locally constant, a very nice map. So the general theory says that we can find an expansion in Fourier using we can find a Fourier expansion. More precisely, what we have is an expansion of this type. So what does the general theory say? The general theory says that for any locally compact abelian group, there is a dual, what we call the Pontryagin dual, that index the characters, which are the things that we see here. The characters are maps that take values in Z2 and return complex numbers in such a way that for a nicely behaved function, as the function that we consider here, we can find this unique expansion. In general, this is an integral, but in the case of the odometer, we have that the dual can be identified with this group. The point is that this is a countable group. So this integral, in fact, becomes an infinite series. And here, this infinite series is determined by these Fourier coefficients. In this case, are vectors, complex vectors. The expansion is unique, and it has all the good properties. It is linear, and it satisfies very good algebraic identities with respect to convolutions, and also it behaves nicely with respect to the additional structure that we have here, which is the fact it is the structure that comes from the fact that this is also Z2 is also a topological ring. And I'm saying all this because if we go back a bit to consider the equation that we have before, this equation satisfies all this algebraic structure. It is first a linear equation. The Fourier transform is a linear operator. Here we have essentially a convolution. So this behaves again nicely with respect to the Fourier transform. And here we have multiplication by 2, which is something a bit tricky to deal, as I was saying, because this is a topological ring and so on, a different structure, but we can deal with that. The point is, once we pass to Fourier domain and we do this kind of expansion, we can find an analog, a corresponding linear relation for the Fourier coefficients. And after doing the computations, we find that this is the corresponding linear equation. Two important things. The first one is that here the sum has 2 terms. We have many terms because we're multiplying by 2. There is something tricky there. I don't want to go into those details, but we have 2 terms. And here we have an A times A matrix, complex matrix. So in some sense, it's very similar to what happens in the usual subdivision case, but we're working now here in Fourier domain and on an infinite dimensional space. Now, as I was saying before, what we want to do here is really iterate the substitution. So we want to iterate the linear relation. And when we iterate it, we get an equation of this type, which is for any k. So here we iterated the equation k times. The only difference with the previous one is that here we have a k, so some other coefficients. In any case, these are explicit coefficients. When we do the computations, we find an explicit formula for these things that depend on the combinatorics of the substitution we're considering. And here we also have a recurrence for this capital phi k. This time the sum has 2 to the k elements. I'm just mentioning this because there is some complexity here that comes from the fact that we have many elements in this term. Yeah, okay. So I call this the Fourier Perron-Fermat equation. And this is what we're going to really analyze. Now, up to this point, everything that I have said is quite general. It works. This is just a consequence of the fact that we're working with a skew substitution in which the associated infinite space is an odometer. But now I want to use a trick which is completely adapted to the case of the Thue-Morse case, In the Thue-Morse case, the substitution satisfies some symmetry that allows us to do the following trick. In general, we have alternative methods, but are longer and more difficult to describe. So here I'm going to use this trick, which is the following. I'm going to say, instead of working directly with these vectors, I'm going to define now a complex quantity, one-dimensional quantity, which is the difference. And this is natural to do because what we want to prove here is that 1/2 is the only solution. Equivalently, this is the same as saying that for this new variable, after doing the change of variable, 0 is the only solution. And of course, this is general, but what is particular to the case of the Thue-Morse substitution is that the previous equation, the Fourier-Perron-Frobenius equation, translates into a very nice equation for this delta quantity, and more precisely, the Fourier transform of this. And we're doing this because, of course, it is easier to prove that the only solution to something is 0 in comparison to proving that the only solution to something is 1/2. And more precisely, it is easier because from this Fourier-Perron-Frobenius equation, we can obtain this kind of inequalities, which I'm going to call here a contracture inequality. So we relate the L2 norm of the nth level with the coefficients that appear here. This time, these are different coefficients that can be obtained from the phi k, capital phi k from before, but these are some coefficients depending on the combinatorics of the substitution, and then some upper level. And what we would like to show here is that this kind of contraction inequality forces 0 to be the unique solution. And this is what we can do because we can check, for instance, using the computer, that capital psi 2 is smaller than 1. And as long as this quantity is smaller than 1, we can iterate the contraction property using some additional tricks. And we get that, in fact, the only solution is the one that has L2 norm equal to 0. So delta hat is 0, delta is 0, and we get the final solution, which is the one that we expected to have. And in particular, we obtain an answer to Deakin's question. Okay, so I still have some minutes left, so I would like to pass to some perspectives. Just very rough ideas, thinking from a broader point of view what is going on here. The first comment I would like to make here is that from a dynamical perspective, what we're doing here as a crucial step is something very clean that I find very interesting. What we're doing here in the topological part, at least, is showing that the symbolic dynamical system generated by Thue-Morse of this 3/2 Thue-Morse work is topologically disjoint from the 2-adic collimator. And it is this that really allows us to prove uniform to obtain some combinatorial symmetries and prove many different things. This is like the nice, concrete, and encapsulated way of describing what is going on here. This system is disjoint from the 2-adic collimator. It contrasts to what happens in the usual Thue-Morse case, because in the usual Thue-Morse case, Z2, this odometer, is a factor, so it synchronizes completely in some sense with respect to the Thue-Morse. The question about whether this is true from a measure theoretic point of view is related to studying factor frequencies, and this is something that we haven't done for the moment. And the second point that I would like to say here is that most of what I have discussed here, as I was saying, depends only on the fact that we work with skew substitutions. In general, this skew substitution can be quite chaotic with the Nicola-Kosky world and so on, but as long as this induced action on the state, on the space of parity sequences or state sequences, as long as this action is abelian, most of what I have said remains quite tractable. In the sense that, for instance, we will get an action on a locally compact abelian group. So Fourier methods make a lot of sense, and they are not horrible to use, as in the profinite completion of the free group general case. Many other things, also the topological recurrence and the topological part, the uniform recurrence, it seems to be at least quite tractable. And of course, the final thing that I would like to say here is to pose some questions. So for the moment, I mentioned some classes of subjects, some classes of infinite words that can be described using fixed points of skew substitutions, the automatic words in a rational base, but it would be nice to have more examples. whether there are more examples, whether there is something that we can look at here. And of course, it is also natural to consider both in the Thue-Morse case and in related examples, finite properties or other kind of properties. And just to mention one that I find particularly interesting is to try to describe a bit infinite spatial world and maybe some symmetries at a dynamical level or also at a more combinatoric on word level, some symmetries of the language. Yeah. And with this, I'm going to finish. So thank you for your attention.
Great. Thank you very much, Bastian. Does anyone have any questions? Hajime.
So thank you, nice talk. And I have a question about the factor complexity of 3/2 Thue-Morse. So your answer is that it has lower bounds for n to the alpha. My question is upper bounds. Is there?
For an upper bound for the Thue-Morse case, you mean?
Yes.
Sorry, I didn't explain this correctly, I think. Yes, I didn't define what this theta means. I forgot. Let me go. This theta means that we have an upper and lower bound at the same time with possibly different numbers.
Sorry. So lower bounds and upper bounds, so except for constant or?
Yeah, except for constants.
Okay, thank you. Thank you.
Thank you.
Are there other questions?
So I have a small question. So in the end, you mentioned that that you think the situation is tractable when the action of B star and S infinity is abelian, but so not just the action on S, but the action of S infinity. So maybe I'm misunderstanding what's happening here, but it seems to imply that basically your action doesn't depend on the actual letters, but it's just like only depends. So it has to be like just model. It has to be just, you're just basically looking at somehow time model n or something like that.
Formally, for this to be true, the action needs to factorize through the abelianization of a B star. So the action would only depend on the parent vectors of the input words.
Right, but isn't it because you want it to be abelian in the sense that the sequence of state is this? Like if I'm applying AB versus I'm applying BA, then I need to have the same sequence of states, not just the same final state, but all the intermediate states also have to be the same. So then it seems like the state I got after applying the first A has to be the same as the state I got after applying the first B in the second one.
That I don't see clearly. I haven't thought much about this. It could be the case. I'm definitely going to think more about this, but I don't see it from what you said.
Okay,
Sorry.
maybe I don't understand definitions precisely, but yeah, okay, thank you.
Yeah, Jeff.
I was just wondering whether or not your methods, I mean, you've shown that the symbols occur with equal frequency, right? So, if I understood right. So, does it say anything about the speed of convergence to the limit a half over prefixes?
So sorry, the question is whether along prefixes this converges to the limit.
I thought that's what you proved.
Yes, yeah, this is what you proved.
But how about the speed of convergence? In other words, if I count the number of ones in a prefix of length n, it's going to be n over 2 plus some error. And what does the error look like?
Yes, very good question. We haven't thought about this, but I know that there are some conjectures, for instance, I think even by decking around the speed of convergence. It could be. I don't know, to be honest.
And finally, do your methods hold out any hope for Kolakowski or not?
As I was saying, the situation becomes so ugly. Uh, I mean, we haven't considered this question that far, but as long as we get like, so the thing is that, for instance, if we get this pro-final completion of the free group, then we can also use Fourier methods. There is something that is called the Peter-Wiles theorem that adapts everything that I have explained here for this non-abelian case. But instead of characters, we need to use finite dimensional irreducible representations. And this set of representations is something that they call wild in this particular case of Kolakowski's, this profinite completion. It means that it is very difficult to understand. So I don't know. It seems hard.
Thank you.
Yeah, Hajime.
Sorry for second question, but so my interest is so 3/2 more to a Morse along squared. In the classical theorem Morse, it's a normal number. How about so numerical experience or something?
We haven't tried. It seems like a difficult question, to be honest, because even in the Thue-Morse case, this is already not trivial. But I don't know. We haven't even considered this direction.
Okay. Thank you.
Shwo.
Yeah. Hi, Bastian. I have just a question concerning your method to prove the equality between the density. It seems that when you apply your Fourier method, you only use the fact that your screw substitution is uniform. I'm not sure, but I have just a quick intuition like this. But do you think your method can be applied for all uniform screw substitution?
In complete generality, I don't expect so, because we know that even for regular automatic words, for regular uniform substitutions that are not skew substitutions, the frequency might not exist. It exists in the logarithmic density sense, but in general, it does not exist. So I would say in this case, we also need some minimum kind of primitivity conditions so that this works. So yeah, that's it. Yeah.
Okay. So what is the point to prohibit that you cannot use the Fourier method for all uniform substitution? At which point that
That's a good question. We don't know. We don't have like even an idea.
okay.
I mean, we have some sufficient conditions that seem reasonable, but like a complete characterization, I don't know. The main point is that here everything at the end boils down to this inequality. And I haven't said anything about what's the structure of this thing. It simply comes from the combinatorics of the substitution. It is a large formula, like an ugly formula that we can put in the computer. Yes, it is smaller than one. But beyond that, we don't have that many intuitions.
Okay, thank you.
Does anyone else have a question? If not, thanks again, Bastian.
Yeah, and thank you for all the questions in general.
And thanks to all of you for coming today. And we will see you all again, hopefully in 2 weeks for the next talk.